I think we should go ahead and get started again on the block 3. This one is going to be talking about engineering systems for sustainability and resilience, really emphasizing systems again. And so I'll turn this over to Sue Noakes, who will be moderating this. And Sue is the Associate Dean at the University of Kentucky and was president of the American Society of Agricultural and Biological Engineering when it decided to adopt these kind of methodologies as a top priority. So Sue, it's all yours.
Thank you, Jim. And thank you to Dr. Singh for that really interesting session of transitioning to circular systems. And now for our block 3 session, our provocateur is going to be Peter Fryer. He is a professor of chemical engineering at the University of Birmingham in the United Kingdom and a fellow of the Royal Academy of Engineering. He is also director of EPSRC, Center for Formulation Engineering, which integrates research in the sustainable manufacture of foods, personal care, pharma products, and fine chemicals. Peter?
Thank you very much indeed. Let's hope the difficult bit, which is always, can people see my screen? Engineering sustainability across the food chain. So what I would like to do is talk a bit about supply chains, how we get supply chains to work, the sort of things that happen in sustainability. I'm grateful for my colleagues Estefania and Seraphim in building this talk. Estefania comes from a farming background and has loved the pictures of big trucks and combine harvesters that we've had up to now. So the supply chain, the thing that it's worth saying before we start is that the food industry really is quite good at the supply chain. COVID disrupted it, but not broke it. So we have a system. The question is, does it work? Does it deliver safe and cheap materials? Are there things moving through it that actually shouldn't be moving through it? You can buy in British supermarkets water flown in from Fiji. You can buy green beans from Brazil or from Egypt. We're actually moving water around, and as we learned earlier, water is a resource. It is finite. We need to be careful. I used to work for Unilever, and we were always told that the greatest food product was the tea bag, because you add 99% of the material at point of use and you add boiling water, so there isn't a micro problem. And you were basically just shipping the bit that made it taste nice. So there are issues in the supply, the moving around of water. The trouble is, of course, if you dry food and reconstitute it, actually that then can become quite unpleasant. So we need to look at how supply chains actually work. I went to a conference in Australia a year or two ago, and the first thing I saw was a pub selling Stella Artois. We have long supply chains. We have huge long supply chains. We've missed out on localism, which our grandparents did. We've gained logistics. There is possibly a different model for supply chains built around everything we've talked about. The graph on the bottom here is looking at all of the possible ways of making food. From the purple line, which is basically making it in your kitchen, to the blue and green lines, which are making it at macro scale. Economies of scale work brilliantly if you have big and cheap trucks, it becomes much more complicated, as it will when the energy costs flip over and we start to look at how expensive transport actually is. Worth noting at the same time that we have very efficient trucks and so forth. Actually, for the rest of the world, the engineering issue is supplying cold, supplying efficient refrigerated systems. So there's new models. What would localism look like? Beer and bread and maybe ice cream do this already. Could we change the model completely and make the thing more circular and more robust? We've talked, people this afternoon have talked a bit about alternative proteins. The rather scary pile of food in the bottom right-hand corner was offered at an EFOST meeting in Vienna a few years ago, and people scraped the mealworms off and ate the bread. But the bread and the pesto are made with insects as well, which raises an interesting question. The economics of making powders, of grinding things through to powders. Grinding is a very energetically expensive operation. It is cheaper to eat crickets, it is greener to eat whole insects than it is to grind them up. Whether the consumer will be happy with that, how it actually works at the consumer level, is something that we need really to worry about. So there are alternative parts of supply chains. There is the beginning of this. There are companies doing this. How will it actually work? And we heard a really nice talk about getting rid of farms altogether, getting into a system where you actually have cultured meat. There are really interesting beginning to be artificial milk products. Good, which is the top left one, just got 170 million of funding. We have to be careful about this. There are beginnings to be products if you look in the biotech literature, because of course the issue is how do you scale this up? The companies at the moment, most of the companies have a much better website than they actually have a product because they're at the burning venture capital stage. But this is something that the engineers, a lot of this has happened without a lot of engineering. We need to work out how this works. We need to work out how these supply chains would operate. So we end really with a set of quite difficult engineering questions. The top line there is from Forbes, not a science journal. This is cell cultured meat meets animal free fermented fat. Dear God, they've just got another 100 million. So there are these new models for supply chains coming through. So the question is, how do you do scale up? Do we really build lots of new plants for these materials? Are there ways in which we can put these through this stuff through existing plant, or do we have to rebuild processes and products from the bottom up? I was always taught as a chemical engineer, if you go to AICHE meetings, you see earnest young men linearizing vast numbers of differential equations, and you have to optimize the whole system. You don't just optimize a bit of this. If you optimize just a bit at a time, you end up with local optima, and local optima are much more hard work than global optima. So we need to bring people together we need to think about it, because as the bottom right-hand corner says, your dinner actually is in the supply chain. So thank you very much.
There we go. Am I unmuted? Yes.
Yeah, I think I've stopped.
Okay, yes, and I'm unmuted. Well, thank you, Peter. That was very provocative. Next, we have Mike Rowe, who is going to give us a perspective on supporting convergence research and development. Mike is the Senior Advisor for the Science and Engineering at the National Science Foundation, and he's founding chair of the U.S. National Science and Technology Council's Subcommittee on Nanoscale Science. Prior to joining National Science Foundation, he was a professor of mechanical and chemical engineering. And he has actually pioneered convergent science and its application to emerging technologies. So, Mike?
Thank you for your kind introduction. I will try to bring the slides. Okay, view full screen. Yes. I will try to address, in the context of this meeting, the topic of convergence with relevance to food and agricultural systems. First of all, convergence is a current trend in knowledge, technology, and society, and it can be used not only for research, but also for transforming purposes. I will try in the time available to speak about the concept of convergence, typically applicable in complex systems, which has a basic principle to facilitate convergence, and implementing convergence R&D. First of all, evolution in nature, science, technology, and society are increasingly turbulent, coherent, and emergent. And the usual methods, sector-based, single approach, single domain, are no longer effective. And so in order to reach a solution and study the problems, one has to have a holistic view. I take, for example, as about what happened in agriculture, a recent book just published, and in the history of agriculture and food system, he wrote that is based on a framework that attempts reorganize nature into deceptive simple components. And complex phenomena in agriculture are simply ignored as irrelevant. Like we look to a single seed, to a single machine, and so something has to improve. What is convergence? Convergence is a problem-solving strategy to holistically understand and transform a system for reaching a compelling goal common for the whole system. An example for this will be like introducing nanotechnology to food and agriculture. That means you can address big topics. The approach includes typically 3 steps: deep integration, formation of the new system, and thereafter formation of the new capabilities from the created system. In a first step, many people think that convergence was look like a just union of people, union of disciplines, which itself doesn't bring benefit. For instance, you have too many people for a simple problem you don't need. However, it's a major step toward reaching a goal. If you look to the right of this slide, the main content of convergence, as we defined in the last 20 years, is convergence toward realizing a common goal in a system. That means the purpose is not to bring two things together, but to realize a goal. In order to realize a goal, you have multiple inputs, you have multiple pathways. You have usually the system, it's complex, could be described by neural networks at best in a general case. You have to look to create, for instance, tools, to create people, to create connections, to interact to surrounding socio-economic system, for instance, to other technologies. And finally, to reach the common goal. That means it's a kind of more a real situation of transforming the system for a purpose. In order to facilitate convergence, we have identified 7 principles. Behind this, there are several theories, and each principle has 3-4 methods, but I will go just to this level of principles. First of all, is holistic view. Anything is connected, in principle, certainly stronger or weaker, by stronger or weaker connections. This interdependence determines a coherence in nature and society. And the challenge is to find unity in diversity. This challenge recalls the purpose of this focus series of conferences. A main step is to have a vision-inspired research for achieving the long-term goals. That means vision is not based on applications, it's not, because the idea is to go beyond the existing application. It's concept problem-driven, typically. We have an evolution pattern. It's typically, we have a convergence toward the system change, divergence, and we have a spiral flow of information and action and innovation among the participating fields. Another principle is that any decision should be based on system logic, deduction, and problem solving. Another characteristic is one has to identify common cross-domain languages, methods, cultures, in order to be sufficiently general and to communicate and to be efficient. Multitasking typically is not a single pathway. You may have 10 pathways simultaneous, and the idea is to coordinate this to a given purpose. In order to have a result, like how people call sometimes in S-curve in the development of technology, you have to coordinate the timing. That means timing is important, the concurrence, and the speed. We have, I give several references just for background. It's an overview that presents the history and the basic principles that we published in 2020, Principle and Convergence in Nature and Society. And we have a handbook where we have 75 case studies for these principles. That means it's no longer something completely new. The foundational report where we introduce the idea of reaching a goal in a system and looking to the whole society, human dimension, was the report Converging Technologies for Improving Human Performance in 2002. And it's interesting, there we developed more than 30 visionary ideas for 20, 30 years, of which more than half are realized and all are on the pathway to be realized. At that moment, I recall that Nature published an article that told this is too exploratory. It looks like Hollywood will never happen, like brain-to-brain interaction. Now, all of these ideas are close to reality. Thereafter, we've done international benchmarking with in 30 countries, and we have a section on sustainable development. And as example of application, we have convergence, growing convergence research at NSF, Convergence Accelerator, and signals in soils. maybe I make a last sentence that convergence is a general strategy to reach a goal in a complex system to either create, improve, or accelerate an outcome. And so it's of general interest, and this domain should benefit from this. Thank you.
Thank you, Mike. Very interesting talk. Thank you, Mike.
Thank you.
All right, next we have Kelly Babbitt, who will be speaking to us on modeling, analytics, and trade-offs. Dr. Babbitt is a professor of sustainability at the Rochester Institute of Technology and is trained as a chemical and environmental engineer. Kelly's research group uses methods from circular economy, eco-design, and life cycle assessment to create sustainable solutions for food systems, consumer electronics, plastic waste, lithium-ion batteries, and renewable energy systems. Kelly?
Thanks so much. I hope the slides are coming through okay.
Good.
All right, great. Thank you all for the opportunity to share some perspectives today on food system modeling. And what I want to share today is really informed by both an NSF-funded Infuse grant and from collaborators on a new sustainability-focused research network, which I hope may in the future be a platform for all of us to collaborate more broadly. Today, I want to make 3 points about the challenges and opportunities of modeling food systems and circular solutions, given the vast complexity inherent to these systems that my many other colleagues today have shared. First, I want to note that the importance of a full system view when thinking about modeling food. This is also sometimes called a life cycle view. Much of our attention often goes to highly visible issues like the leftovers or spoiled produce we throw away at home, or the food insecurity so dramatically revealed by the COVID pandemic. But the reality is that these issues are only the tip of the iceberg, and measuring the food system requires that we consider the full farm to fork life cycle, from food production, processing, packaging, distribution, and ultimately the way the food is consumed in both commercial, institutional, and residential settings. Let's look at food waste as a key metric of this life cycle sustainability and efficiency. Our current practices lead to over 35% of all the food generated in the United States ultimately being wasted. This carries a huge price tag, over $160 billion. And it also represents the loss of all of the nutritional value in that food and the resources that went in to producing it, whether they're fertilizers, chemical pesticides, land, and water. Now, when we scale these issues up to the global level, we see that the life cycle environmental impacts are even greater. When we look at food, both as what is consumed and what is lost along the way, this represents about 25% of global greenhouse gas emissions and 90% of biodiversity loss. Now, these metrics underscore the importance of this holistic life cycle view, both when measuring food systems as they are now and when considering different potential scenarios of circular economy transitions. So life cycle assessment is a formalized method that provides such a trade-off. This allows us to first define a system of interest and all of the processes that encompass it, then quantify the chemical, energy, water, resource inputs to each of those processes and the resulting emissions out to natural environments, and then ultimately quantify the risk that these emissions and resource uses create to human and ecological health, considering impacts all the way from climate change to freshwater ecotoxicity. Now, this method is particularly critical for proactively evaluating circular economy solutions, because as has been mentioned today, these can lead to unintended consequences and trade-offs. Let's take the example of anaerobic digestion. This is a promising solution that can help close resource loops by valorizing food waste or converting the carbon and energy contained within it into biogas, which can then be combusted as a fuel for electricity or cleaned and compressed and injected into the natural gas pipeline, potentially to be used for transportation. Now, life cycle assessment has actually shown that this technology reduces greenhouse gases from landfilling food waste and reduces the emissions from the fossil fuels that the biogas displaces. However, it also determined that this process produces a side byproduct, a liquid digestate that is nutrient rich and has the potential to be land applied as a replacement for synthetic fertilizer. However, depending on management practices, this can actually lead to downstream emissions of additional greenhouse gases or nutrient pollution into sensitive ecosystems. Finally, we also have to recognize that engineering solutions do not exist in isolation. And this, taking again this biodigester example, this might mean that this creates social and economic considerations, such as the policies that set the price of carbon and energy in a given area, as well as the infrastructure required to collect and transport food waste. But these issues are much more pressing when we look at some of the early stage circular economy interventions, such as those we use to narrow resource loops by preventing food waste from being generated, or those we use to slow resource loops by retaining the nutritional value of food for extended human use. These have immense economic, workforce, and equity implications. And thus it is imperative that our modeling can jointly analyze circular economy solutions, as well as their potential ripple effects into social and economic systems, governance and institutions, ecological systems, and interacting infrastructures. Some of these solutions may actually create tensions depending on what you're measuring. If we reduce food waste too far, we can make a very efficient system, but if the operations are too lean, they may not withstand system shocks unless resilience and equity are built in proactively. Thus, we have an immense challenge and an opportunity to advance new modeling approaches. We need models that can analyze scenarios of both gradual food system transitions and disruptive shocks like COVID-19 that lead to a new equilibrium point. We need models that can evaluate trade-offs between very hard to measure concepts like resilience, equity, and circularity. And we can also look to models from the field of industrial ecology that seek inspiration from the way that nature has evolved over billions of years to solve some of these same kinds of resource and waste cycling challenges. However, food systems and the solutions that can be applied appropriately in given places vary widely from one region to another. And one of the critical challenges in the past is that a lot of research in this area has been focused on specific case studies. We cannot simply carry out an infinite number of case studies, but rather we have to look to methods that can be generalized across different food system typologies that are operating in different regions and places. And finally, these methods only work with high quality data, and data is always a pinch point here. We have some good data, say about the amounts of waste generated in college cafeterias or at retail stores, but not as much about the food flows and the waste that happen upstream, those that happen during manufacturing, and what really happens during consumer behavior, both at home and in commercial settings. And so there's a critical need for greater data that can help us to understand these food and waste flows, especially how they vary from one place to the next or over time. We need better data about the performance and efficacy of different circular economy solutions and their attendant environmental resilience and equity impacts. To do this, however, we kind of have to step away from what we as engineers find comfort in terms of quantitative data. So there's actually a considerable need for qualitative data that reflects the lived experience and the knowledge held by stakeholders who have firsthand experience working in this space. This may be the people stocking the grocery shelves or serving the food, or the farmers working the land. Our new NSF research network seeks to advance data collection, architecture, and dissemination, and I hope that many of you will be interested in collaborating with us to meet these challenges. Thank you so much for the opportunity to share these perspectives today.
Thank you, Callie, for that very thought-provoking presentation. And the final speaker in block 3 will be Richard Miller. And Richard is going to talk about education and human development. Richard was appointed president and first employee of the Olin College of Engineering in 1999, and he served there for 21 years. Just last year, he served as the Jerome Hunsaker Visiting Professor of Aerospace Systems at MIT for that academic year. And previous to that, he was Dean of Engineering at the University of Iowa. Miller has served as chair of the board on higher education and workforce of the National Academies of Science, Engineering, and Medicine, and as such has come to talk to us about education and human development. Richard?
So thank you, Daryl. Next slide, please. My whole role in this is not as an expert in agriculture, but is someone who spent some time thinking about getting young people to work together on problems that matter and having developed innovations in their work that will carry with them through the rest of their lives. So we're not going to make progress on this problem unless we get the right people together and we get them to work together as a group. I'm going to start this by telling you a small story, which I think will recur as a theme. When I was about 50 years ago, when I was an undergraduate at the University of California at Davis, I had a summer job as an engineer with the Public Works Department in Fresno, which is right in the center of the valley in California that is so well known for agriculture. I had learned how to program computers with Fortran programming in those days. And you see they had just developed a new computer, a PDP-11, I think, and they were looking for people who could use it. So they gave me the job of locating the ideal coordinates, the XY position for the new landfill that would take care of the solid waste needs for the county of Fresno. This is a linear programming problem. Some weeks later, I had an answer. What was fascinating is what they did with it. The director of public works went immediately to a public hearing to present to the public what the advanced technology and digital computing told them was the right answer. And you see, I had been asked to minimize the cost to the public because that's what the Public Works Department thought their job was. Immediately upon presenting the results, two hands went up. One of them was from a person who said, "Do you realize the location for this landfill is within a mile of the ranch of one of the members of the county board of supervisors who has to approve it? Did you recognize that?" Next hand went up and said, "Oh, the coordinates for the transfer station in the inner city where the local trucks transfer the stuff to the long haul trucks is right where you put the jail last year in this minority community, and we're tired of being taken advantage of by the wealthy community in the suburbs." What did I learn? Note to self, engineering is actually not about differential equations. It's about people. And we have to continually remind people of that and keep the narrative and people in front of us as we talk to those around us to deal with complex systems. So to start with the right people, we have to draw them to the problem. And I'm going to be saying what a lot of people have said, much more sophisticated ways than I have, but in ways that are in fact easily understood by undergraduates and by people who are studying English or sociology or other subjects. Next slide, please. So to give you some sense of where this is going, if we're going to produce graduates who generate innovations, this might be, for example, a meeting today among folks in engineering who sit in that blue circle in the upper left. And all of us has a bias in the way we look at problems. They're about applied science. On the other hand, there may be a meeting somewhere else in the country with business and economics officials who are looking at similar problems through the lens of what's viable. And then there, of course, every night on the news, culture, politics, and the media is talking about and shaping the public's appetite for what they want to see done. Now, Daryl, if you'll click this once for me. Now, click again. And click again. And click again. And click 2 more times. My point is innovation, which is the application of original ideas and insights that have value in ways that change the way people live, which is what we need to have happen on the planet, always happens at the intersection of all 3 of these independent communities. They have to be feasible and also viable and also desirable, or people are not going to change their ways. So we need to think about the way we produce engineers so that they're aware of this. And in one head, we have an awareness of all three circles. Click once more, please. No amount of emphasis on narrow specialized courses will produce the innovators we need. It's this breadth of experience that is really critical. Next slide. So let me give you a little tour of how you might talk to a group of undergraduates about this problem. Click, please. This is a little story of history of farming in America, which brings us to the crisis we're at today. The first click again. This is a graph of the percentage of Americans in 1800 who lived on farms, about 90%. Click again. Percentage in 1900, it's dropped to 40%. Click again. The percentage in 2000, that little tiny sliver, 1% of the people in America produce the food, which locally grown at least, contributes to our food sustainability. Click once more. Here's the problem. This is the population growth on the globe over all of recorded history. And you can see in the last 100 years or so, we've had this explosion in population, primarily because we in technology and in medicine have found ways to reduce the death rate, and which is wonderful. Nobody wants to die early. And of course, that's extended the lifespan, but we have to feed these people. This has led to a lot of concern in the past. By the way, I personally am close to this problem. I think for 4 generations, my family's been involved in farming in Central California. Today, I don't think any of my extended family is involved in farming. So we flipped from the blue part of that pie chart to the orange parts about 50 years ago. Click again. In 1970, about the time Earth Day showed up, there was a scientist at Stanford named Paul Ehrlich who wrote a book called The Population Bomb, who put 2 and 2 together looking at these graphs and predicted that there would be massive starvation in the world. Turns out that didn't happen because I think our community in science and engineering realized the potential of, for example, nitrogen fertilizer and mechanized farming to increase the production of food. And so click once more. Click once more. There we go. We forgot about Paul Ehrlich, and we think we've got it solved. And of course, now we're finding that we've just bought some time. Click again. Farming in America has faced system crises before. This is not the first time. And if there are people who happen to have a farming background, they will know this pretty well. Click again. A story which might be pretty easy to get undergraduates to notice is the story of the Dust Bowl by Ken Burns. This was a fascinating documentary that he put together. In my case, it turns out that 3 of my 4 grandparents were born in Oklahoma, including my mother, who migrated to California during the 1930s. Click again. Click once more. The whole system starts with farmers, and it involves politics, economics, and culture as well. So for example, there are lots of buried problems in these graphs. This narrow little 1% slice of the pie that's involved in farming today has enormous implications in politics. For example, we've already heard an excellent talk about water supply in California. It turns out that as the water supply for the farming has been going down, different political groups have been pressing the government for their special interests, including, for example, biodiversity, who is saying, please don't divert the river water to agriculture because it might reduce the biodiversity in the streams. But there's a lot more people involved in the biodiversity movement than in the agriculture movement because of that efficiency in farming. So that predisposes it against success. Click again. So what we need to do is to change in a fundamental way the skill set that engineering graduates have in order to deal with problems of this kind of complexity. By the way, this kind of complexity is not about advanced differential equations and control theory. This is about the complexity of working with people who have a completely different worldview than you, who may be turned off completely by fancy words that we use that have a technical root in them. So we need to develop, first off, a talent competency about what we're dealing with agricultural systems and the innovations, but also a multidisciplinary competency by personal experience in working outside of our discipline of engineering, an understanding of an entrepreneurial and business competency. Nothing is going to sustain as a long-term innovation in society unless it's financially sustainable for the farmers. And let me stop there for a second and point out those on this call probably know this already, but a lot of people in undergraduate population don't. In the area in Central California where I grew up, a lot of farmers are considering selling their water rights to Los Angeles, where the demand is high. It's a one-time capitalization, and then converting their farm to solar farms and then selling the power to the electric grid. It turns out that it's almost financially viable to do that in some regions. What does that mean to the long-term production of food? That land is permanently eliminated from productivity. Understanding the business entrepreneurial dimensions as seen through the eyes of the farmers is critical. And of course, a multicultural competency and a social consciousness as well. These are solutions that are aimed at solving problems for all people in society, not just farmers, not just the wealthy people in the cities. Okay, click again. One of the approaches that has exactly this set of goals for teaching young people is the Global Grand Challenges Scholars Program, which was started in 2009. Today, there are 93 university programs around the world, and 42 new ones almost here. Click once more, last slide. Co-designing with decision makers is a method which might be of real value. Here you would start with undergraduate students on 5 to 6 on a team with non-engineers. A lot of people talk about multidisciplinary projects, and they mean they'll put a mechanical engineer and an electrical engineer to work together. I'm talking about bringing a person from a different institution, using farmers, call 10 farmers, ask them about the problems they see, and co-design a pilot project with them. Okay, I know I'm over time, and it's been a privilege to meet with you today. Thank you very much.
Thank you, Rick, for that interesting perspective on education and what we need to do to create our future engineers.